intro into our day 5 notes is going back to something you guys had in 9th grade. This is our 9th grade notes that you guys had. I made them. Aren't they beautiful? Yes. You should totally remember this. Your real number system. So we're hopping back a couple years here. See if you guys remember this. Your number system always starts first with your natural numbers, which are 1, 2, 3, 4, 5, 6, 7, 8. Those are the numbers that you first start learning when you're learning how to count when you're a little baby. Like my daughter Madeline, as we go up the stairs, we count 1, 2, 3, 4, 5, 6 until we get up the stairs. It's where you naturally start counting. Unless you're Madeline, then you start at 2. But generally, you start at 1. So then after your natural numbers, you have your whole numbers, which adds the number 0, but then it's also the 1, 2, 3, 4, 5, 6, 7. So it's all of those ones. And then after your whole numbers, we add in the integers, which then includes all of the negative versions of your whole numbers. And then after your integers, we have what we call the rationals and the irrationals. Are any of these words sounding familiar? A little bit, hopefully. Your rational numbers are fractions. Integers are rational numbers. Decimals that end or decimals that repeat a pattern are rational. Your irrationals are like pi because it's a decimal that continues on forever and there's no pattern to it. The square roots of non-perfect squares are irrational numbers, again, because they have decimals that continue on forever and don't repeat. But all of these groups fall under what we call the real number system. And that's what you've dealt with this entire time until today. There is another kind of number that we are going to be dealing with, and it is called an imaginary number. Yeah, we're getting into imaginaries. So, all real numbers so far until today, we're dealing with an imaginary number. So, an imaginary number is any number that can be expressed as bi, where b is just some number, and then you've got an I attached to it. So, for example, 3i is a pure imaginary number. It's got the 3 and it's got the I. A complex number, however, has a real number attached to the imaginary number. So, like, for example, 4 plus 2i is a complex number because it's got the real number 4 and then it's got the imaginary 2i. Putting them together makes it a complex number. So now, the way we get the I is by taking the square root of a negative 1. Remember, up until now, we always told you couldn't take the square root of a negative number. That's because it creates an imaginary number. It creates the imaginary I. So when we go and we try to take the square roots of negative numbers, which you will now be able to do, you just have to remember that one extra step. So for this one, 25 is already a perfect square. What would be the square root of 25? 5. But because it has the negative in there, that makes it imaginary, so it would become 5i. So here, for this one, when I take the square root of my negative 4, well, what would be the square root of 4? 2, but since it's negative, I'm going to add the I to it, and you have to multiply it times the number that was out in front. So there, our final answer would be 3 times 2i would be 6i. So then for C, though, 48, is that one perfect? No. So it's the same rules as before. What would be the perfect square that goes into 48? Not 6 and 8. We need a perfect square. Not 36. 4, yes, but that's not the largest one. 16. Now, because it's negative here, the negative stays with the perfect square, and then the 3 goes after it. So now, just like we did for the other ones, what is the square root of negative 16 going to be? 4, and then I, because it's negative. But we got to multiply it times that 3 halves that was already there. So 3 halves times 4 be 6i. radical 3. But then we just got to bring this back down. So we have our complex number of 5 plus 6i radical 3. So far, the only thing we've done differently is if it's negative under a square root, it just turns it into an I. So now what you're going to have to do sometimes is you're going to have to do some arithmetic using your I. So you have to add them, subtract them, multiply them, divide them, all that good stuff. So we have what we refer to as the powers of I. The powers of I, they follow a pattern. And it's a pattern of 4 numbers. I to the first is just going to be I. I squared. Remember, I is the square root of negative 1. But if I square that, what happens with my square root and my square? It cancels. So I squared is actually negative 1. I to the third would be negative I. I to the fourth is a whole number 1. How what? So I to the third, right here, I to the third is the same as I to the first times I squared. Can we agree on that? Yeah. So I to the first is I. What did we say I squared was? So I times negative 1 is negative I. I to the fourth I can break up as I squared times I squared, which we said was negative 1 times negative 1. So it equals a positive 1. And then it just keeps following this pattern. If I were to do I to the fifth, that would equal I. I to the sixth would be negative 1. I to the seventh would be negative I. I to the eighth would be positive 1. And it just keeps going through that loop. So the ninth would be I. 10th would be negative 1. Negative I, 1. And it just keeps going through and through. So a lot of times they're going to ask you to simplify your powers of I. So the way we do that is you take your exponent and divide it by 4. So divide exponent by 4. So what happens when you divide your exponent by 4 is sometimes you get a whole number, sometimes you get decimals. So what happens is if you get a decimal, we'll make a little column here, decimal of 0.25 when you divide, that means it's equivalent to I to the first. And I'll show you what that means when we go through a couple of examples. It'll make a little more sense. When we divide and we get 0.5, that means it's the same as I squared, which is negative 1. If I get a decimal of 0.75, that means it's the same as I to the third, which is negative I. And then if we have no decimal or 0.0, that's I to the fourth, which is 1. So I promise, with examples, that makes a little more sense. So with example 1, we have a 23. So in your calculators, I want you to do 23 divided by 4. What did we get? 5.75. So there's our decimal, 0.75. What did I tell you 0.75 was the same as? Negative I. 0.75 is I to the third, which is negative I. So that means I have 8 times a negative I there. I can replace I to the 23rd because I'm reducing it down, which 8 times negative I would just be negative 8i. That's how we simplify our i's. So for B, we got 2 of them to do this time. So 22 divided by 4, what do we get? 5.5. So we got 0.5 as our decimal. 0.5 means it turns into a -1 because it would be I squared. I squared is -1. Then we'd have 3 times, okay, now we got to do 13 divided by 4. We get 0.25, so that means it changes into what? 0.25 turns into I to the first. So I get -1 plus 3I. All right, let's try example C. Let's take our exponent, divide it by 4. Let's see what decimal we get. 0.25. So that means I to the 41st is just like I to the first. So that's going to be an I. I squared, we don't even need to divide that because we already know I squared equals what? -1. So an I to the 17th. 0.25 again. So 0.25 is I. So then here I need to distribute my -3. -3 times -1 is 3. -3 times 2I would be -6I. Do we have any like terms? Yes, we have our i's. So 3 has to go first, and then what's I minus 6I? -5I. You always have to put your I second if there's another number there. So again, those i's, they always follow that pattern. I, -1, -I, and then 1. So sometimes we need to add, subtract, and multiply and divide with our i's. It follows the same rules as all of your rules of exponents. You just have to reduce at the end using your little chart that we did, the powers of I. So here, what are we doing with our two binomials? Subtracting. But what do I have to do with this subtraction sign? You got to change those signs. So this becomes +2 minus 3I, and then you can lose the parentheses. A lot of people forget to drop those parentheses. So now you just have to combine your like terms. -3 plus 2 gives us a -1. 7I minus 3I gives us a 4I. That's going to be our final answer. You don't want to leave it if it's an exponent higher than 4. You need to clean those ones up. All right, so example 2. We got to first do like what we did on the front. We got to simplify this. So -49. When I take the square root of this, what do we get? 7I. Square root of 49 is 7, then it's negative, so you get your imaginary I in there. And our square root of -4 would be 2I, but I have to do it times that 2 that was there. So that makes it what? 4I. So 7I minus 4I gives us a final answer of 3I. So example 3, we have some distributing to do. You got to do the 3I, the 7, and then the 5I squared. So 3I times 2 gives us a 6I. But then the 3I times -5 gives us a -15I squared. It follows the same exponent rules. I times I, you add those exponents, it gives you I squared. 7 times 3 is 21. 7 times I gives us 7I. So then 5I squared times 2I would be 10I to the third. So now we have some things to clean up. I squared, what does that equal again? -1. So that means it's really -15 times a -1 for that. So that's going to make it a positive, yep. So then 21's fine, 7i's fine. I to the third, what did that equal? -I. So I just converted my I squared and my I to the third. So I have 6I plus 15 plus 21 plus 7I minus 10I. Then we can combine all like terms. Numbers first. 15 plus 21, 36. And then your I, 6I plus 7I minus 10I, 3I. What do you think we have to do for example 4? We're multiplying. We got to do some distribution here. So we got to do 4 times 2 first. That's the easy one. But I don't want to do 4 times my square root of -40 or 49. So what do I change this into? 7I. So I want to do 4 times my 7I. What does that give us? 28I. And I want to clean up my square root of -25. What does this turn into? 5I. So 5I times 2 would give us a 10I. And then 5I times 7I is 35I squared. So again, I squared is the same as what? -1. So really I have a 35 times a -1 there. Which what do we get when we do 35 times -1? -35. So my 8 minus 35, what would that give us? 8 minus -27. And then 28I plus 10I would give us 38I. And that would be our final answer. So just like before, you can't have radicals in your denominator. You also cannot have i's in your denominator. So if you have a single term, like in example 5, you have to rationalize your denominator by multiplying the top and the bottom of your fraction by whatever's in your denominator. This is just like what we did with our radicals. So 3 times 2i would give us a 6i. And then in our denominator, 2i times 2i would give us a 4i squared. Which again, what does the I squared equal? So when I do -1 times 4, though, I really have a -4 in my denominator. So can I reduce this at all? Yeah, I got a 6i over a -4. We'll just rewrite that. What can I divide those both by? 2. So 6 divided by 2 gives me 3i. -4 divided by 2 gives me -2. So then on example 6, does anybody remember what we would multiply that one time since it's a binomial? There was a word, started with a C. I heard somebody say it. Conjugate. What would our conjugate be here? Remember, you just got to change your sign in the middle. So we would have to multiply times 2 minus 4i. Your conjugate just changes that sign. So we have a whole bunch of distribution to do. 1 times 2 gives me 2. 1 times negative 4i gives me negative 4i in my numerator to start with. Three I times 2 is 6i. 3i times negative 4i gives me a negative 12i squared. And then we have to distribute in our denominator also. 2 times 2 gives me 4. 2 times negative 4i gives me a negative 8i. 4i times 2 gives me a positive 8i. 4i times negative 4i is a negative 16i squared. So we got to clean this up a little bit. Again, I squared equals what? Negative 1. So in my numerator, I've got negative 12. This is really negative 1. So negative 12 times negative 1 really makes that a what? Positive 12. So my 12 plus my 2 would give me a 14. And then negative 4i plus 6i would give us a plus 2i in our numerator. In our denominator, what happens with our 8i's? They cancel. And again, I squared is negative 1. So negative 1 times my 16, though, makes it positive. So 4 plus 16 in my denominator gives me a 20. Then we have to reduce. What number can I divide 14, 2, and 20 by? 2. So 14 divided by 2 is 7. 2i divided by 2 would give me a 1i, or I could just write it as I. 20 divided by 2 is 10. So that's our final answer for that one. So then, with your imaginary complex numbers, you can actually graph them also. When you go to graph these, your x-axis is like it normally is. That's your x-axis. But your y-axis, they actually refer to as being yi. That's the one you use to graph your imaginary number on. So, if I go to graph, for example, 3 plus 4i, the way I would do it is I would count over 3 on my x-axis, and then I would count up 4 to give me the 4i. So this number here is your x. That number there is your yi. So then the only thing you do is you connect from your origin to wherever your point is. So this would be our graph of 3 plus 4i. Other thing that happens is what they like to do is they call this line right here, they call that a vector. Just so you know what that's called. That's a vector. So the other thing we do with our vectors is they want you to find the magnitude of it. Pretty much that means find the length of our vector, which since it's a diagonal line, can I easily find the length of that? No, it's not like I can sit here and just count the boxes and tell you how long it is. What we end up using is we end up using the Pythagorean theorem for it. You kind of finish off your right triangle here, where this side's 3. That side of it is 4. And then you can calculate the magnitude of your vector that way. So it would be 3 squared plus 4 squared equals x squared. X being our magnitude that we're trying to find. Or if you happen to remember this one's a triple. Yeah. This one, your magnitude should be 5. But again, if you did the workout, this would be 9 plus 16 equals x squared. So 25 would equal x squared. And then you take the square root of it, so 5 equals x. Now they do also have a formula for it if you want to memorize it, but that's just another formula for you to memorize. Where it's just the square root of a squared plus b squared, which if you think about it, which is what we did. We took a squared, added it to b squared, and then took the square root of it. Because it's not always going to be a triple, but that's how we find our magnitude. That's actually kind of easy. All right, questions, comments?